Next up in Chapter 5 is Section 5, which deals with Dalton's law of partial pressure. Dalton's law of partial pressure says that the total pressure of a mixture of gases is equal to the sum of the pressures that each gas would exert if it were alone. So the total pressure equals the sum of the individual pressures of the gases. If we're looking at this picture here, you see you have a blue gas and an orange gas. And if we were trying to determine the total pressure of those gases in the container together, we could look at the pressure of those gases individually first and see that and add them together to find the pressure of the total. There are a couple of things to consider and keep in mind when we're talking about partial pressures. So the fact that the identity of the gas molecules is not important, meaning it doesn't matter what they are, it just matters what their pressure is, it implies a couple of things. One is that the volume of a gas molecule must be insignificant. And two is that the forces between the molecules must also be insignificant. So let's look at a pretty common example for a Dalton's law problem. So here we have an apparatus that's got two ends and it's closed. The connecting part between the two ends of this container is closed. So both sides of this container has helium, but since they are separated and closed, they have different pressures. So you've got one side of the helium container that has a pressure of 2 atms and 9 liters, and another side of the helium container that has a pressure of 3 atms and 3 liters. After the valve is opened, what's the pressure going to be of the helium gas? There are two ways to solve this problem. The first is to start on the left side and find the new pressure of the gas after the valve is opened using a P1V1 equals P2V2. The way you would set that up is you could say, well, my initial pressure, my P1 is 2 atms, and my V1 is 9 liters, and set that equal to your new pressure, what you're looking for, times the sum of the two volumes of the container. So you've got 9 liters plus 3 liters, which makes 12. If you were to do that math, you would see that the new pressure would be 1.5 atms. Do that same thing for the other side, so find the new pressure of the gas on the right side after the valve is opened using P1V1 equals P2V2. So you would say 3 atms times 3 liters is going to equal the new pressure X times the total new volume, so 9 plus 3, and you would see that that is 0.75 atms. The total pressure, therefore, is going to be 1.5 plus 0.75, which is 2.25 atms. The second way that you could solve this problem is to find the number of moles in each chamber separately using PV equals nRT, add the number of moles and the volume together on each side, then use the PV equals nRT again to solve for the new pressure. Let's look at another example. So in this problem here, we have 27.4 liters of oxygen gas at 25 degrees C and 1.3 atms. And we also have 8.5 liters of helium gas at 25 degrees and 2 atm. And we're pumping them both into a tank that is 5.81 liters at 25 degrees C. The first part is calculate the new pressure of oxygen. If you can pause it here and try and do that. One hint for you, if you're not sure where to start, is to use P1V1 equals P2V2. Okay, so if you were to have solved that out, P1V1 equals P2V2, you would start for oxygen, 1.3 atms times 27.4 liters is going to equal the new pressure, what you're looking for, X, times the new volume, 5.81 liters. And you would see that the new pressure is 6.13 atms. Next up, you would want to do that same thing for helium. So pause it here and try and do that. Using P1V1 equals P2V2, you could find that 2 atms times 8.5 liters is going to equal the new pressure you're looking for times 5.81 liters. And the new pressure would be 2.93 atms. The total pressure is therefore going to be a sum of those two individual pressures, 6.13 plus 2.93, so that's 9.06 ATMs. There's one other piece of Dalton's law problems that you need to be aware of. So first we're going to take a little step back. First off, mole fraction is something you should be familiar with. Mole fraction is just the number of moles of whatever you're interested in over the total number of moles present. And if we were to apply the mole fraction into our ideal gas law, we could find that the mole fraction is also equal to the pressure of the individual gas over the total pressure. And what that means is that if we didn't know the individual pressure of a gas, we could figure it out by multiplying the total pressure by the mole fraction of that gas that we're interested in. So for example, and I know these words are small, but basically what we have here is air is 78.08% nitrogen, 20.95% oxygen, and 0.934% argon, and 0.0345% carbon dioxide. Calculate the partial pressure of each gas in a sample under 5 ATMs of pressure. The way that you would do that is say the partial pressure of nitrogen is going to equal that percentage times 5 ATMs, right? We're looking at the mole fraction. So it's going to be 3.9 ATM. Partial pressure of oxygen is going to equal that percentage times 5 ATMs, and so on. And that is it for section 5.